Section 3.3.
Logarithms.
All right, so the deal with logarithms is when we talk about inverse functions and we have this exponential function y equals to the x, inverse functions means you switch the x and the y around. And so you do that and you go, oh no, how do I solve that for y?
I need it to say y equals, Steve.
Yeah, how do I get that to be y equals?
It's right next to it.
Oh, we write it as a logarithm instead. So that's exactly what logarithms are. They are inverse functions for exponential things.
Is that a rebel insignia on your
It's
Band-Aid there?
Angry Birds Star Wars
Angry
from my
Birds Star
paper
Wars.
cut earlier today. So
Good move.
So what happens whenever you rewrite this as a logarithm is this is our base, right? And we've talked about that.
So it's a log of base 2.
Yeah, this is where our base goes. It's the little number. And then it's like you go in a circle. You don't go to the exponent next. You go over here and you write x. So log base 2 of x equals y.
Yeah. Here's another way to think of it. A logarithm equals its exponent.
Right. So
what's the exponent here? Y. So
yeah,
a log
so it
has to equal y.
the exponent. And then we
And it
have
has to have a base
2.
of 2, which just leaves one other place for that x.
Right.
There you go.
So what are we supposed to be doing on this example?
You want to draw
Graph
out
this?
you want to graph out
Okay.
a little logarithm action there?
So do we want to graph both of these and check out the fact that they're inverses?
Sure.
Okay,
that sounds fabulous.
If we plug in 0 here, we get 1.
You get 1. And it's exponential, so it
And
shoots up on the right and gets really close, but never crosses the x-axis on the left. You know, if you walk from where we're currently sitting,
You said that in an earlier video.
you don't know what I'm going to say.
Okay.
If you walk from where we're currently sitting and do 2 to the x, by the time you get to that wall over there, you'll be way up in space.
That's great. That's so great.
It's like that movie Gravity.
Yeah?
They were up in space.
Yeah, they were. So log base 2 of x. How do we go about thinking about this? Like if we were to try to do it without our calculator and we plugged in values.
Ugh.
Don't say
Oh,
it
sorry.
like
What I
that.
meant to say was, no problem. No problem, Mrs. K. Steve.
Log base 2 of 0.
No deal.
Because 2 to there's no
2
power.
2 to what power equals 0? And it ain't happening.
Right, so this is undefined.
Yeah, undefined. And if you'll notice on the graph that we just drew, it never actually crosses the x-axis.
Right. So what we're doing is since these are inverses, then we should have a reflection over the line y equals x.
That's
okay.
pretty close.
It's okay.
Pretty close.
All right, so if we were to plug in 1,
Yes.
then we'd be saying 2 to what power is 1?
0.
Okay, so 1, 0.
Yeah, I like it.
And the other way to go is if we'd made a table of values for this one, we could just flip
switch
the x
them.
and the y. That would have been handy. But
That would have been
well.
really handy, but we didn't do it, and that's okay. We're all good here.
If we plug in 2, 2 to what power is 2?
The first power, 2 to the first power is 2.
Okay, and then hopefully you can get an idea because these are supposed to be reflected that this should go this direction.
Yes, yep.
And this should
Now,
go...
as fast as an exponential equation grows, a logarithmic equation grows just that slowly. So we could actually look at a log base 2 of 1,000 and get a y value of like 10 or something like that.
Right.
Like that's not out of the question.
Right. That's true. So we have this note here that a common logarithm is a logarithm with a base of 10. When we have a base of 10 here, sometimes we don't actually write the base.
Most times, actually.
Yeah, so if you see log without a base, there is a secret 10 here. And then natural logarithms, which is ln.
Logarithmic and natural.
Yeah, it
sounds French.
Something like that. Those are actually a log with a base of e. Like
right.
Those two together, log and
Make a
base of
natural
e,
log.
make a natural log. So.
And it's called a natural log because, believe it or not, those numbers and ratios show up a lot in nature.
Go figure.
Yeah, it's amazing.
Yeah.
Going between logarithmic and exponential form.
Super handy.
I mean, super is not even close to.
Super duper.
I mean, pretty friggin' handy.
Because sometimes it's more useful to have something as a logarithm, and sometimes it's more helpful to have it in exponential form. And in either case, you always want to start with the base, wherever it is, and then go in a circle. For example, if you're doing y equals log base b of x, you start with the base, and then you go in a circle. That's not where I meant to draw that to. B to the y equals x.
And remember, a
big deal.
logarithm is equal to its exponent, so that should help you organize a little bit what's going on.
Right. So if we're trying to evaluate logarithmic expressions without using a calculator, on each of these we need to set it equal to some variable. That's going to help us out, right?
Yes, I agree.
And then you can think of this without actually like literally rewriting it, but I like to rewrite
I
it.
do too, because I can in my mind work out 6 to what power equals 1 a lot better than I can work out log base 6 1 equals.
Right. So we start with the base, which is 6. We go around and say it's 6 to the x equals 1. A little circular fashion here. Always start with the base. Okay, so 6 to what power equals 1?
X would have to be 0 in that case.
It would. Anything to the 0 power is 1.
Yay!
All right, so let's see what else they can throw at us. Here we have equals
3
x.
to the x equals 81.
So 3 to what power is 81?
3.
No.
4.
Yes. 3 to the 4th power is 81.
Dang it.
Okay, how would you go about figuring that out if you didn't know?
Well, if you didn't know, what you could do is just ask yourself, what's the square root of 81?
You could, and you get 9.
Yeah, what's the square root of 9?
3.
And how many 9s do we have?
2.
So 3 times 3 times 3 times 3?
Okay. Another option is you could just trial and error. 3 to the first, 3 squared, 3 to the third, until you come up with it, because these are growing exponentially, right? They're growing exponentially.
They're growing
We have to have
exponentially.
something happen between like 1 and 10 probably.
Right.
Pretty sure. Okay, so this is log, and this does
Oh
not
my
have a
heavens.
base.
That's a base 10.
Okay, so let's make it equal x. So this is 10 to what power equals the cube root of 10.
Can we rewrite cube root of 10?
Let's do that.
That's 10 to the 1/3.
10 to the 1/3.
Oh my heavens to Metsies. I know what x is.
Yeah,
That's 1/3.
because there's this property that if these are the same, these bases, their exponents have to equal each other.
So,
So x equals
chitty
1/3.
chitty bang bang, 1/3.
Does that look like a 3?
That-
I don't think
is that
that
a
looks
snow?
like
What
a
was
3.
that? Was that a snowman?
Did it? In honor of our most recent ice storm
Do you
in
want to
March?
build a snowman
Well, it's
or ride our bikes around the hall? Oh, you haven't seen Frozen, so never mind. Forget I said that.
I've watched Gravity last
Let me
night.
not rub that in that you haven't seen it yet. So
Yes.
remember, this is like log with a base of e to the third.
E to the 3rd.
So if we rewrite this, this is e to the x equals e to the third. So again, the bases are equal.
Bases are equal.
So your computer is tripping on
I don't
me.
know why you all of a sudden can't write good.
I don't know why you can't speak English good.
I mean, that's why I teach math, K. Steve, Mrs.
Yeah,
K. Steve.
yeah, you do. Okay, so this is log base e.
Oh my, that's.
What if we mess with this?
Can we
Right
mess
now.
with that?
Can
Let's
we
mess
mess
with
with it?
that. Let's
Okay.
make it negative 1/4.
Okay. So you're saying it's e to the negative 1/4,
Yes,
right?
that's what I
So
say.
let's go back in slow mo.
Okay, slow mo it down.
So that what we have is 1 over e to the 1/4.
Right, because the 4th root of
That's
is 1/4
the-
power,
Yeah, and then we move it up to the top.
which means that the exponent goes from positive to negative.
Right. So in slow mo, that's what just happened. So that's equaling x, and we do
E to the x
e to the x
equals e to the negative 1/4. I happen to know what x is.
Yeah,
17.
negative 1/4.
That's what I said.
Yeah. Awesome.
Okay, good stuff. Good stuff there. Calculators. No calculators yet again. What are we doing to these children?
Trying to torture them.
I like it.
Okay, I believe this is example 3, and so we've got all these properties of basic logarithms, common logarithms, natural logarithms. They're all the same. They just look slightly different based on like whatever's going on. If
Right.
we have a base, that's what the basic properties are. Anytime that whatever number this base is, if you have a 1 here, it equals 0.
Every time.
Every single
And
time.
so if you'll look at the other two common logs, natural logs, it has the same property.
Right, log of 1 equals 0, ln of 1 equals 0.
Because we're talking about a specific base on those.
Yes,
So.
yeah, we are. And then if we have log base b of b, where those two numbers are the same, it always equals 1, because b to the first power equals b. And so,
B is B is B is B.
so what you can think of is if you have like log base 3 of 3. I like to think of it like because those numbers are the same, they cancel out, and
Right.
that is 1.
That is 1. Yes, I
Okay,
agree.
what do we do when we cancel? We have to put a 1 in its place. So that's what's happening there. And then in a similar way here, this log with a little b to the y, those are gonna cancel each other out and leave us with what the exponent is.
Right.
Okay, like here, the exponent would have been 1, right? So
Right.
it leaves us with the exponent.
Right. Just leaves us the exponent.
Or if it's b to the log b of x, well, since those are the same number, then it's like that cancels out.
Right. And all you're left with is just whatever the exponent is, just that x.
Right.
So,
And these other two boxes say the same thing.
and they say the same thing, but they're giving you now a specific base that you could see frequently.
Yes.
Still the same stuff. No trickeration going on.
Right. So these are actually really easy. On the first one, 7
Is that
to the
yellow? Is it going to show up?
I meant to pick a different color. Sorry.
there, okay.
7 to the log base 7 of 3. Well,
The 7s cancel. Yep. Hey, that was like a boomerang shaped thing.
so this equals 3.
Yes.
So 10 to the log of 9.
Well, there's a hidden 10 in that guy.
So
He's a common log. So again, they all go away, and you got 9.
e to the ln of 6.
6, because that ln is the same thing as log base e.
So the bases match
So
up.
the bases match up. You cancel everything out. You're left with a 6.
Awesome. Example 4 and 5. Hey, use a calculator to evaluate the logarithmic expression if it is defined, and check your result by evaluating the corresponding exponential expression.
Log of negative 5.14 is not defined. Just mark it out. Thank you.
Well, I'm not going to mark it out. I'm going to write the answer, which is undefined.
Okay,
So,
whatever.
and the way you know that is that all of our logarithms, natural logs, whatever base it is, no matter what, our logarithm has a domain of
Greater than
than
0,
zero.
but not equal to 0.
right. So, logarithms have a domain of not equal. Not equal. Sorry,
Yes.
0
Don't pull a
to
student
infinity.
move here, okay, Steve.
And then the range, just to throw it out there, the range is negative infinity to infinity.
Now, but it certainly doesn't look that way when we're talking about range. It looks like it has an upper bound, but it doesn't.
actually keeps going
it's
up.
fake. It's a fake upper bound.
Right, and one of the easiest ways to think about this is what is the domain and range for an exponential function?
Yes.
Because it's just flip-flop.
It's just the
For an
backwards side,
exponential, the domain is negative infinity to infinity, but the range, we have an asymptote, so
Right.
that makes it be 0
Right.
to infinity. Anyway, log of 9.43. There's a button on your calculator that says LOG.
Log.
That's the button we want.
Yep.
So log of 9.43.
Because this is log base 10, and when you punch it in your calculator, it's log base 10. Now, if you've got a fancy dancy calculator, it will give you a logarithm template that you can fill in. So depending on if you have Inspire or if you're using the most current version of 84, it might ask you to put a number in for the base.
Right, it may give you, whenever you press the log button, it may give you like a box in a box, right?
Yep.
And so if it gives you two boxes,
You
you
got
have to remember that this is a log with a
Yeah.
base of
It's
10.
not a log base of 1. That's
No, it's a log base 10.
Yeah. So there you go.
And there is a way to get to that on the 84s if you have the most current operating system, but it doesn't default to that.
Right.
All right, so if you type in log of negative 5.14, it will give you an error.
It gets you an error message. Yep.
So that is helpful to you to know that that's what that means, is that it's undefined there. So
Right.
natural log, on the 84s, you have to press second and then the log button, or
Yes.
it may be somewhere slightly different on the Inspire, but you should be able to find it, and you
I'm
get
just looking for the little ln in there,
1.3.
and it's going to be 1.3987. And you want to go 3 or 4 decimal places with logarithms, because with logarithms, as it turns out, those decimal places can be significant.
all the difference. Yeah, earlier today I was helping somebody on a problem, and they had only put 2 decimals on something, and it gave them an answer of like 18. I had put 3, it gave me an answer of 15. Those are nowhere close
Yeah.
to the same thing. Like
Right.
that's not good enough. That's a life or death situation. If this were if you were doing math in a life or death situation,
And
it's not close enough.
Yeah, Final Jeopardy, you'll lose.
Yeah.
That,
Yeah.
that could be life or death
Yeah.
right there. So we don't want to make any Final Jeopardy mistakes.
No.
Okay.
Example 5. Solve the equation by changing it to exponential form.
So here's what I would do.
Okay.
That's a 10 that we don't see, again, because
Yeah.
it's a common log. So I would just rewrite that sucker as 10 to the 4th equals x.
You know, that's exactly what I would do.
Really?
Yeah. Do you know what 10 to the 4th is?
10 times 10 Times 10 times 10. So you just add a 0 for every 10 you got in there.
Right, there's 4 zeros.
Yeah,
10 to the
10,000.
fourth is 10,000.
That's pretty cool, monkey beans.
That was pretty simple.
Mm-hmm. Yeah.
How about this one?
10 to the negative 1. Yeah, that's going to be
Equals-
0.1. That's 1/10.
Yeah, 10 to the negative 1, you move that down to the bottom and make it 1/10
And
equals
it's-
x. Or you
1/10.
could put 0.1, which is 1/10,
Right.
whichever. Okay.
It's all good. There you go.
Let's analyze some functions.
I feel like we analyze a lot around here.
We do. That's a big thing in mathematics, actually in life in general.
What?
So
Say it isn't so.
we're going to do the common logarithm log of x and the natural logarithm, which is log base e of x, and it would look very similar.
They look awfully similar.
Actually, like, is there a difference?
I don't see a difference.
All right.
But there's got to be one because those are different bases.
So it must have to do with, what do you think, maybe the rate at which they increase?
You know, it's quite possible the rate at which it increases.
I don't know.
What the difference is.
I don't know. Or maybe it's a very, very small differences. Who
Yeah, maybe
knows?
so.
So
Okay.
domain for log of x.
It's going to go from 0 to infinity.
Right.
You
Okay,
cannot
because look
include
at the
either one
x
of those,
values.
right?
There's a vertical asymptote here at 0, and then it's going to the right, so 0 to infinity. The range.
It goes from negative infinity to positive infinity. Now, this is almost a trick question because when you look at it, it certainly doesn't look like it's going towards negative or
Right.
towards positive infinity.
Right, but if we could keep going forever and ever and ever,
Forever and ever.
it would continue to increase the whole time.
Right, the whole time.
So, continuous?
Yes,
Okay.
totally continuous on its domain.
So should I just put on its domain?
Yeah, that's fine. It also increases the whole time.
So increasing
Increasing behavior from negative infinity, from 0 to infinity.
positive infinity. Okay, bounded.
It is not.
No, because our range is from negative infinity to infinity. One of those has to not be there for
Right.
it to be
So
Bounded.
they're both there.
not bounded.
No extrema either because there's no maximum or minimum value with this since it continually increases.
Right. And so this, yeah, totally. Symmetry.
It's got no symmetry. It has a vertical asymptote at x equal 0,
Right. Which
but
we
it
mentioned
doesn't have
earlier.
a horizontal one because it's not bounded.
Right.
Okay.
And then the end behavior,
It actually approaches infinity as x goes to positive infinity.
as x goes to positive infinity, it goes to infinity.
We can't really do negative infinity here because we don't approach negative infinity.
Oh, you're right. We can't, because look, it gets stuck.
Yeah.
We don't ever get towards negative infinity.
Yeah,
so
so-
that other limit, you could either write it and
Doesn't
say it's
exist.
undefined, or it does not exist, or just, I guess, not write it.
Yeah, I mean, what we have written is fine. So, hey, guess
Is
what?
anything going to change?
There's nothing that's going to change. Even though these are two different logarithms, they are still logarithms. They're bound by the same
the same.
general rules,
Right,
which would include all of these. So we could just copy all of those answers, paste them all over there,
right.
and that's, yeah, there's no need to write it all again. But sometimes in the teenage brain, there is a massive. Does that say samesies?
Yeah.
I like it. There is a difference between log x and natural log x, and it's really there is not much of one.
There's not.
They're
It
both
would
logarithms.
be like we say there's not a lot of difference. If you actually are computing values, there is a difference.
There is a difference.
And you wouldn't want to use one instead of the
Right.
other.
If you're building a bridge and you need to use log 10 or a common log, please do that. Don't use the natural log.
Right. But I mean,
But graph
Other-
shape and
graph shape is very
behavior and all of that are.
so then we could look at this and say, well, what if we do a vertical shift, right? Or a
Right.
vertical stretch, or what if we reflect this? And those are going to be similar transformation rules
That
as
is
to what
correct.
we've already done.
Right.
So,
Righto. What are we doing today?
all right, describe how to transform the graph of y equals ln of x into the graph of the given function. Sketch the graph by hand and support your sketch with a graphing calculator.
And all of the rules that we're going to follow for these are the same rules that we've followed every time we've graphed a function.
Every single time.
Every single time.
So let's describe.
We're going to reflect over the x-axis there.
No,
The y-axis.
The y-axis.
The q-axis.
no.
The the r-axis.
Stop guessing. Reflect over the y-axis. Anytime you make x negative, it does the opposite of what you think it would and makes it reflect over the
When
y-axis.
you work inside of the function, it's going to have an impact left and right.
Yes. Okay. And then this is a shift up of 2.
Updos. So I'm just going to double check those on my graphing calculator to make sure that you draw them out the way they're
Right,
supposed to be drawn.
a natural logarithm, it goes through at 1, 0, okay? And then, so what we're doing is we're reflecting over the y-axis, which would put it over here, and shifting up 2, okay? And then the shape of this graph, it looks kind of like this. Oh, by the way, well, I guess I'll talk about this in a sec once you have the graph up. All right, so we are reflecting, so that puts it over here. But then we're shifting up to.
You drew it the wrong way. It goes that way.
That was the initial graph, and I'm messing with it.
I looked down for a second, and everybody goes crazy on me.
No one went crazy.
Man, that's almost awkward.
Okay, so that I got a little close to 0 there, but
it's not touching. It just
not
looks
touching,
like it.
and then it goes that way.
There you go.
If you graph it, it should look like that. Here's what our graph looks like right here. You think they can see that?
Probably not, but that's okay.
Okay. Well, the important thing is, even on the Inspire, which is super fancy, it makes it look like the graph stops, but it doesn't.
It doesn't stop.
And
it keeps going.
Some of them are really bad. Like the 83, it'll like show you something that looks like that. And no, if it's a logarithm, it keeps going down. So keep that in mind.
Yeah, if you draw a heartbeat on this, then heartbeat shape where you just start, stop, or a bumper.
Yes, this should not look like a heartbeat in any way, shape, or form. All right, so this time we are making x negative again.
Oh,
so that's
for the love
reflect
of Pete.
Over the y-axis.
But we're also moving at 5 units.
Okay.
But +5, which means -5, because you do super secret opposite society.
What did you type into your calculator?
Negative. I typed in. Well, why are you questioning what I typed in?
Left 5.
Yeah.
Because it's a +5.
Right. What'd I say?
But because these are both horizontal things, the order here does matter. And what you want to do is you want to start off by, which way is it? 4. So you want to start off by moving it and then reflecting it.
Yes.
We move it. It normally would be here, so we're going to move it 5 to the left. 1, 2, 3, 4, 5. So that puts it here. But then, we're going to reflect it.
Oh, yeah.
Which means it's really over here.
3.
At 4. Right? So that means that it's going to go in this shape.
Right.
And that can be really confusing.
That can be a toughie.
Whenever both of those are combined and the order matters. But in general, you want to do the left or right first and then reflect.
Mm-hmm.
So
you can always factor out the -1. You can make it natural log of -1 times
but then you'd have
x
to
minus 5. And that might help with some of that because now the -5 part stands out and you see.
Right. It just depends on which way you want to memorize doing it.
Right. Yeah, you get to pick it. You pick it.
Example 8. Hey, you know what we haven't had?
Lunch.
True, but I meant a code word.
Code word lunch.
Okay. So, code word lunch.
Man, lunch.
I think I've just lost Mr. Hazelwood to lunch. All right, example, but as long as he doesn't lose his lunch. Okay. Describe how to transform the graph of y equals log x into the graph of the given function. Sketch the graph by hand and support your sketch with a graphing calculator. Do you mind?
What's the matter?
We need to.
Did you want something?
No, I'm good. We need to finish the video.
Oh my God. I don't know whose that was, but it's really bad. Okay. I'm not hungry for lunch anymore.
All right, so this is Negative on the outside is reflecting across.
The x-axis, because anything outside of the function is going to have an impact up or down.
Okay. And there's a vertical stretch of 2.
Yes.
And the negative on the inside means that it also reflects across the y-axis.
Right, so you have to really pay attention here or you're going to wind up in some sort of wacky place. I mean, it's true. I mean, you don't want to wind up in a wacky place graphing a logarithm.
No, you don't. So we want to remember, if we're sketching it by hand, then we want to think about, okay, well, what does the logarithm do? It does this deal.
Right.
We want to reflect across the x-axis.
Right.
And so this time the order should not matter because we're not doing anything that's going to affect something else negatively.
Right, because we're just flipping.
Right. So we are reflecting across the x-axis, so that makes it do this.
Right.
Gonna take that and vertically stretch it 2. That means it just is wider, right? And so mainly this is what's gonna look different.
Right.
Okay, and then...
And with a logarithm, a vertical stretch is sometimes not very noticeable, just because it grows so slowly.
Right, absolutely. Reflect across the y-axis now, so that flips it this way.
Flip
and so
pinky.
that means that, let me find my last color here.
Flip the pinky.
That we will still be...
Go through -1. That's important.
And so it should look most like the pink graph.
There you go. That's
Okay.
pretty good. That's not bad, actually.
And you don't have to graph all those steps in between. I just think it's easier to think of if you do the steps in between.
If you can see them.
Yeah, and if you can just jump straight to the last one, that's fine. Whatever you got to do what you got to do. You know what I'm saying? All right, so.
All right, coming up. This one's a little trickier here.
Oh my. Okay, so what have we got? We've got I'm going to start from left to right. We reflect over the x-axis again because there's a negative out there on the outside. We have a vertical stretch
by 3, so it makes it.
And then we have on the inside shift left of 1.
Yep.
Which we want to do before we reflect.
Right.
Over the y-axis. And then last we shift up 2. And the part here that's the kicker is this right here. That's
where the trickeration can occur.
I think I just said shift up 2, but that's totally shift up 1 because that's a 1.
That's totally a 1.
That could have completely thrown us off.
But it might not have. Let's graph this sucker and
get your elbow out of my face.
Getting really hungry too, K. Steve.
Don't open that again.
Look at the date on that. Whose is this? October 3rd, March 13.
Just leave it alone.
A year old. It's been in my fridge a year. I don't remember putting it there.
So this is what our normal logarithmic graph looks like. Let's go ahead and do the shifts. Let's shift up 1 and left 1, which puts our point here.
Right.
And then we're going to reflect over the x-axis and the y-axis.
Right, a little reflective action.
So when we reflect this way, it just makes it point this direction.
The other direction.
Let me draw that.
Yeah, draw that.
So it's going
to be...
Well, that was a little... And that's with the vertical stretch, too. That's
yes.
One reflection, and then we got to reflect down.
Right.
So that puts our point down here.
Now it just reflects right over that spot, I think.
Over that spot?
Yeah, right there. Just reflect it right there. You're perfect. Everything's perfect. Now just reflect.
But
right there. Just go. Go for it. There it is. Ready? Go. And anytime now. Anytime. Yes. Yes. There you go. Good. And there you go. There it is. It's what the that's what the calculator says.
Okay, so that blue graph is your last one. Okay.
It's your last one. Okay.
Sorry. So this all being done with, this is like the most complicated we could get, just about, right?
Yeah, and it took us some
some time, some thought, some effort.
Yeah.
They won't all be like that.
No.
But can you do 2 things at once?
Oh yeah, maybe even 3.
Maybe even 3, because that's going to be important. But you shouldn't
Right.
have to do 5 things at once.
No.
But be prepared for 2 or 3 things.
Definitely, and you can always use your calculator to help you out a little bit too, because
Right.
you'll start seeing some of the patterns when you.
Right, especially if it were to be on a no calculator part of a test.
Right.
It would be something really simple.
Yes, well, within reason, relatively.
Yeah,